Hello and welcome back. In this video, we are going to go over the current mechanisms that we have in semiconductors. And this is a different topic than what we already covered regarding the fact that in semiconductors, we have both current due to free electrons or electrons in the conduction band, as well as currents due to movement of electrons in the valence band, because we have holes, which looks like a positive charge movement or a Hall current. So let's go over current flow mechanisms. By current, what is current? Current has to do with movement of charge, right? And in terms of, if we were to do a classification here, or the mechanisms, there are two mechanisms which cause the movement of charge in a semiconductor. One of them is due to electric fields, and what you have is drift currents. Drift currents are movement of free electrons or movement of holes due to some electric field. Okay? And we also have diffusion currents. These are currents, meaning movement of charge due to differences in concentration of free electrons or holes in the material. And this is it. This is the reason why those mobile charge carriers that charge free electrons or holes, the reason why you're going to have a current, a movement of charge, is either going to have to do with electric fields or concentration. So let's put that here. Electric fields, these differences in concentration. Okay, there's a gradient difference in the material. Okay, so with that, let's learn a little bit more about these concepts. And for that, let's start with the first one, drift. Currents. So if we do a draft of a material, let's say here, actually, since I'm going to need to use a cross-sectional area, I'm going to do it in 3D. If this is a semiconductor material, silicon base, okay, and in the material I have some free electrons inside. Okay, these are electrons that acquire enough energy in order to go from the valence orbit all the way to the conduction band, or from the valence band to the conduction band. And you also have holes. I'm going to represent them like this, as positive charge actually. Okay. And what happens if we connect an external electric field? So we connect here a battery, for instance, right? This is an electric field. Here we have positive charge, negative charge. So this is a difference in potential. Effectively, we are putting positive charge in one edge, negative charge around here, right? Well, what we're going to see is that the electrons, they're going to start having movement of electrons. Movement of charge causes current. Similarly, and those are electrons in the conduction band, similarly you're going to have movement of electrons in the valence band, which are also moving this way, but that looks like a positive current going the other way, a positive, right? The holes being attracted to the other side. Now, this electric field, our convention is that the electric field points in the direction that a positive charge will move. So the electric field is pointing this way, in this case, right? And so we have electron current in the opposite direction and Hall current in the direction of the electric field, like that. right? So let me actually write it, holes and electrons. Those are going to add up to create a current. Now, and this is, I want you to understand the concepts first. I'm going to do a little bit of math here, not as important. The velocity due to drift of the holes, P, is given by the mobility of the holes times the electric field. Okay? Similarly, the velocity due to drift, sometimes we do n drift or just Pn drift, is the mobility of the free electrons times the electric field. It's an equation that you should know. The velocity is proportional to the electric field, and then there is a mobility constant. This mobility, you should know that the mobility of electrons tends to be around 2.5 times the mobility of holes. Okay? Electrons in the conduction band, free electrons, move faster through the silicon material than the holes, meaning that the electrons that go from atom to atom in the valence band. So I think that this is something that you should know, as well as the general equation for the velocity. It's a good result. With that, we could create an equation for the current, but maybe we can do that later. Well, actually, let's do it. The current due to, say, holes, if we were to think of a cross-sectional area here, okay, this is the cross-section with an area of A, right? What will be the current? It will be the area that you have times the charge times the concentration of holes that you have times the velocity, right? How many of those go through that area? Or if you substitute here, you will have A times charge times the concentration of holes times mu P times E, or sometimes we look at the current density, where you do the current per unit per cross-sectional area. And so the A cancels and you have Q, P, mu, P, E. Similarly, we can do this. This is for holes, for electrons. I n is equal to A times Q, concentration of electrons, times V electron, right? And so what will we get? Actually, we need to do a negative sign because it's in the other direction. Oh, and over here I should have put a minus here because the velocity is opposite to the electric field. Let me back up. And so what you get is that minus and this minus here that I missed before cancel. So you're going to have A Q times N times mu N times the electric field. And therefore, the current density in the case of holes, you get Q, the charge, concentration of holes, mobility of, Q, concentration of free electrons, mobility of electrons times electric field, and therefore the current due to drift, the drift current, is the sum of the two, the current due to the holes plus the current due to the electrons, which is Q times, so the charge, concentration of holes, mobility of holes, plus concentration of electrons times mobility of electrons times electric field. And this thing here sometimes is expressed as the conductivity. So A equals the conductivity electric field. Really what you need to remember is that the current is proportional to the electric field by a conductivity, right? Sometimes you can see this also as the inverse or rho, the resistivity, is equal 1 over the conductivity, right? And you can talk about that the resistivity is equal to the electric field over the current density, like Ohm's law. Okay. So let's back up for a second. What were we looking at? Drift currents. What are drift currents due to? Movement of charge due to electric fields. The velocity of those charges is proportional to the electric field by a constant of mobility, what we had here, right? So you have the general equation V equals mu times E, so proportional to the electric field, how fast they move. In the case of holes, same direction as the electric field. In the case of electrons, opposite direction, and this is why here we have minus, right, to the electric field. So we know how to calculate a velocity given an electric field and the mobility. We also know that the mobility of electrons is higher than that of the mobility of holes, 2.5 times. Based on this, for a cross-sectional area, we are able to calculate a current or a current density. In the current density, or the total current, you add the two together, and the result is simply that the current density is proportional to the electric field by a constant that tells you the conductivity of the material. Good enough. Okay, so let's look at now, quickly, at drift currents. At diffusion currents. I have mentioned that in the case of diffusion currents, they are due to differences in concentration, meaning if we were to plot this, we have a material and for instance, you have, let's consider a lot of electrons, free electrons. So, but you have more in one side than throughout the material. So if we were to plot, for instance, the concentration, in this case, as a function of x, so x is here, okay? And this may happen, for instance, if you have an electron injection or hole injection. Okay. The concentration of electrons in this case, imagine, goes like this. If you have a gradient in the concentration, you're going to have movement. Okay? These electrons are going to tend to move. For one thing, they repel each other, but the other thing that they're going to move through the crystal due to diffusion. And the equation for a diffusion current will be Jn equals the charge of the electrons, the diffusivity of the electrons, and then it's going to be the derivative of the concentration that you have, right, the gradient that you have in the concentration as a function of space. So this will be for electrons. This is what you will have for holes. We'll look at the concentration gradient, P. Current, of course, the total current will be the sum of the two in a situation like that. And I also wanted to go over a relationship which is Einstein relationship between the mobility of holes, the mobility of electrons, the diffusivity of holes, the diffusivity of electrons, and the thermal voltage. And this is a cool equation, is that the diffusivity of free electrons over the mobility of free electrons in the conduction band, there's a ratio to the diffusivity of holes to the mobility of holes. Okay, remember, and this is equal to the thermal voltage, and the thermal voltage is given by K, okay, times T over Q, okay? And if we were to plug this T 300 at room temperature, the thermal voltage, which we will encounter a lot in electronics, is 25.9 millivolts, okay? So this is an important equation here. Remember, in this case, we are talking about what? Diffusion currents over here. Okay, these are diffusion currents due to difference in concentrations, like here. Okay. Over here, we are dealing with drift currents due to electric fields, and we have a constant here that is the thermal voltage. So in summary, let's wrap up. We have two current mechanisms affecting both free electron currents and Hall currents, meaning electrons in the valence band. By current mechanisms, we mean fundamental causes that will cause those charges, mobile charges, to move, either due to electric fields, like here, and that will be a drift current due to electric fields, or to differences, gradients in concentration of those mobile currents. Those will be diffusion currents, differences in concentration. In the case of currents due to electric fields, we have an equation for how fast those carriers of charge are going to move. Here we have it. It is proportional to the electric field, and then you have a mobility constant. Okay? In the case of Hall currents, same direction of the electric field. In the case of electron, opposite direction. That's where we have a minus sign. Which one moves faster? Well, free electrons around 2.5 times faster than holes. With that, for a cross section, here we are able to calculate a current. Area times how much charge you have times the concentration of holes or free electrons times the velocity. You plug it in. Or equivalently, we can do a current density where we look at by cross-sectional area, the total current density, you add the two, and you get it. Big result. The current is proportional to the electric field, not a surprise, and a conductivity, which depends. That conductivity is going to depend on what? The concentration of doping of holes, the concentration of doping of electrons. The more you dope, the more conductive is the material, and then the mobility of electrons and holes. Okay? Diffusion. I did here a difference in concentration of electrons. There could be also a holes and a difference in concentration. The idea is that in this case the current density is proportional to the gradient of the respective concentrations that you have. Okay, this is for free electrons. This is for holes. Okay. of course, the amount of charge that you're moving, and the diffusivity. And then finally, Einstein's relationship, the diffusivity over the conductivity for electrons, diffusivity over conductivity for holes is a constant and equals the thermal voltage, which is 25.9 millivolts for silicon at room temperature, and we will use that result significantly. Thank you.